So we'll begin a discussion of aldehydes and ketones today and complete it during our next lecture. But we're moving on to another group of molecules that we're going to have a higher priority than everything we've seen so far. And that's the general trend we've been doing as we build up different types of molecules in this course is they tend to get more complicated, either more reactive or more oxidized. And that's where we're going today, all three of those things. So we have to remind ourselves where we've been. And so far you've covered everything on this slide except for the last two. Right? So we've covered hydrocarbons with the multiple bonds or single bonds and so forth, all the different halogens you can add to it. We've discussed alcohols, we discussed ethers, and now we're going to finish out this chart with aldehydes and ketones. Now there are other things we're going to add after that, but to finish out this chart so far, we need to cover aldehydes and ketones. Okay, and so what is an aldehyde and a ketone? So if you briefly look at the molecules down there, you notice that they have all those aldehydes and ketones have one thing in common, and that they have a carbon that's double bonded to oxygen. Okay, this is the next oxidation state in that molecule. So in every case we've had before, we've had carbon only making one bond to oxygen, or in some cases zero when we didn't have an oxygen. But we've only ever had one bond between the carbon and the oxygen. And now we're going to have that be a double bond. We're going to have two bonds between the carbon and the oxygen. This is the first of these molecules we're going to see. So that's the important part, or the functional part of this, and it's called a carbonyl. So this carbonyl is just an oxygen that's double bonded to a carbon. And that's all this means. So the little box on the right is a description. There's many ways to look at it. Here's a box of it where we have just the C and the O isolated. This is called the carbonyl. Of course, the oxygen only makes two bonds. They're both to this carbon, so it can't be bonded to anything else. And the carbon makes four bonds, as usual, and two of them are to the oxygen, so it only makes two other bonds. Okay? Here's another way of representing it. Same thing. Here's the carbonyl, and then it makes two other bonds to whatever they might be. We call them X and Y here. And in our model kits, you can see the same thing. It's kind of weird to show it this way, but it's how the model kit works. It's the carbon double bonded to the oxygen, and then it makes two other bonds. Okay? So the geometry around this carbon would be what? What is its molecular geometry?
Trigonal planar.
Trigonal planar, exactly. So it has three Vesper groups. It still has four bonds. One of them just happens to be a double bond. So again, three Vesper groups, no lone pairs, and it has a trigonal planar geometry. Those older topics are not going away. Right? We're going to keep building on everything we learn. So don't just forget everything after an exam. Okay? So in these cases, all these molecules that have these carbonyls in them, the carbon will still make two other bonds. What those two other things are classifies it as either an aldehyde or a ketone. Right? So in the case of the alcohol, you notice there was only a single bond between the carbon and the oxygen, so it does not have a carbonyl. But aldehydes and ketones do, and here it is. Now, it may not always be drawn pointed straight up like this, right? So keep that in mind. But the two other things the carbon is bonded to are either going to be carbon or hydrogen generally. Okay, so it could be a member of a longer chain, or it could just have a hydrogen. If these two things, X and Y, whatever they might be, if at least one of them is still a hydrogen, we call it an aldehyde. Okay, so hydrogen, aldehyde, right? If neither of them are hydrogen, we call it a ketone. Right? They both can still be hydrogen. That would be a very simple one, still an aldehyde, as long as one of them is. If neither is a hydrogen, so both of them being carbon chains here, right, then it's called a ketone. And that's the only difference between aldehydes and ketones, right, as far as their structure. Right? Aldehydes always have at least one H on this carbon. Ketones have none. Right? If you have two, yes, it's still an aldehyde. You can't have any other number. Okay, so let's see how we distinguish these two. The one at the top is an aldehyde, and one at the bottom is a ketone. So let's follow our rule to make sure it makes sense. I've boxed in the part you're looking for. So look for the carbonyl, and then ask, on this carbon, is there at least one hydrogen? In fact, this one has two, but yes, there's at least one, so it's an aldehyde. Here's an example on the right. Right, so this is the carbonyl. It's often drawn this way. You don't always see this carbon. So it's double bonded to this oxygen. And then this carbon is bonded to this carbon chain and this hydrogen. So yes, there's at least one H. This is an aldehyde. At the bottom, we find our carbonyl once again and ask, is this carbon bonded to any hydrogens? In this case, no. Right? This is poorly written on the side. It should be the H's in front of the C, but we'll forgive them for now. Right? But it's bonded to this carbon, not the hydrogens, and it's bonded to this carbon. Right? As in this molecule on the right, this carbonyl, the carbon of the carbonyl is bonded to no hydrogens. There are two carbons here. So this would be a ketone. So as long as there's at least one H, we call it an aldehyde. If there are no H's on this carbon, it'll be a ketone. That's the only difference in the two. Otherwise, they're very similar. So turn to the back of your notebook or wherever you're making your priority list. That started at the bottom with just hydrogen, and then you wrote everything else or everybody else above that. And if we haven't mentioned it yet, it belongs in the everybody else category. And then above that, we listed some things like triple bonds. And then above that, we wrote double bond. And then we finally introduced oxygen, and we called it alcohols, right? So that hydroxy group of alcohols gave it top priority. We're going to add to the top of that list now. So just above alcohols, I want you to write ketones. So ketone is the next highest step above alcohols. And then right above ketone, you're going to write aldehyde. Right? So the highest group so far should be aldehyde, followed closely by ketone, and then alcohol, and then double bond, then triple bond, then everybody else, and then hydrogen. Why was double bond above triple bond? We said it was more reactive. Same rationale here. Aldehydes are above ketones because they're more reactive. Okay, so that's your priority list right now. So we need to learn how to name these things, which are aldehydes and ketones. So why can we not make cyclic aldehydes? Can anybody come up with a reason? Look back at the structure of aldehydes. Here's an example. Why can't this carbon of the aldehyde be a member of a ring?
Because it's not attached to another carbon.
Well, it could be attached to another carbon, like it is here. Right? It doesn't have to be
it will make more than 4 bonds.
Right. In order to be a member of a ring, you must make 2 bonds to carbon. Right? You got to be members of a ring, and that would require no hydrogens on it. Or if you try to put a hydrogen on it, like you just said, it would have more than 4 bonds, which is not possible. So that's why aldehydes cannot be in rings, because there's only room for 2 bonds here, and one of them must be an H. So you can't be a member of a ring if you're an aldehyde. But ketones most certainly can, because they have 2 other things that can be members of rings. Right? So these carbons could continue and form rings like this of any size. So ketones can be cyclic, but aldehydes cannot. And it's for the same reason. The aldehyde must have a hydrogen, so it leaves only one other bond. That's not enough to be a member of a ring. And ketones can, because they have exactly 2 other bonds, so they can be in a ring. Okay. So let's go over the basic rules for naming them. And it's really the same rules you've been learning all semester. We just keep adding to the top of our priority list. So number 1 has always been the same. Select the longest continuous carbon chain. But you always look for your priorities. In this case, the carbon of the carbonyl, right, the carbon atom of the carbonyl group, so these carbons, right, must be in that main chain. And not only must they be in it, for an aldehyde, they must be the first carbon, because it cannot be in the middle of a chain. It can't be bonded to more than one other carbon, so it must be on the end. Right? So that should make sense why aldehydes have to be number 1 carbon. So wherever I start, it must be number 1, because it can't possibly be in the middle of a chain. That would necessitate having carbons on each side, and we know it can't do that. Right? So we always start counting the aldehydes, the carbonyl carbon of an aldehyde, as number 1, and find the longest chain. That makes it fairly easy. How do we change the ending? Like everything else, we changed the E at the end to Al this time for aldehyde. Right? We changed it to Ol for alcohol. We use Al for aldehyde. So when you hear me say these, I'm going to stress the Al a little more than you normally would in conversation, so you can hear the ending. So you can definitely hear the difference when I say alcohol versus ethanol, for instance. Right? So an ethanol versus an ethanol, you can hear the difference when I say it. Right? And then as before, we locate and name all the substituents as everything else. And everything else that's not an aldehyde at this point is a substituent. It's all been demoted to losing the race. There's no prizes for second place. Okay, so if you have a double bond somewhere, doesn't have priority anymore. This aldehyde does. Okay, I would say double bond, but it's a double bond to oxygen. That's quite different than double bonds between carbons. Okay? There are some common names, which I don't want you to memorize a lot of common names. In fact, I'll give you very, very few of them. But some of them you've heard of. Like when we did alcohols, you've heard of isopropanol. But the IUPAC name is technically 2-propanol. Right? So I want you to learn a few of the common names. And here you've probably heard of formaldehyde before. It is the simplest aldehyde. But its technical name would be what? There's a picture of it here. What would its IUPAC name be? We call it formaldehyde all the time. But what is its IUPAC name? Find the longest continuous carbon chain.
Methanol.
Methanal, exactly, with this Al ending. So like methane, we changed the E to Al. So this would simply be methanal. And that's what I'll call it on your test. But just so you know, it's just for your information, it's commonly called formaldehyde. You may have heard this name before, right? It's the simplest aldehyde there is. The next simplest aldehyde would be to make the carbon chain 2 carbons long instead of 1, right? And it's called acetaldehyde, right? Often mispronounced, where Americans pronounce the T here as a D, but it's acetaldehyde. But what would its IUPAC name be? Find the longest chain. Say again?
Ethanol.
Ethanal, exactly. So like ethanol, but instead of OL, it's an AL ending, right? So this would be carbon number 1. This would be carbon number 2. Right? And as you've seen with many of our other molecules, when we involve a benzene ring, it tends to adopt a special name. And that's what we'll do here. This one, I say it's a common name for these, and it's also the IUPAC name. So it's kind of the same here. It's often referred to as benzaldehyde. Right? It's a benzyl group, which is a benzene ring with 1 carbon on it, much like toluene was, but it's not just a methyl out here anymore. It's actually an aldehyde. Right? So it's just called benzaldehyde. Right? And this is used as a preservative in many things like foods or canned goods, animals, tissues, whatever you like to use. Same thing as formaldehyde. So aldehydes are generally really good at preserving tissue.
Can you repeat what the second one was?
So the second one, the IUPAC name would be 2 carbons long, so ethane, and then we change the ending from ethane with the E to ethanal with an Al. Drop the E and add Al.
Thank you.
So 2 carbons long, eth is the prefix, so ethanal. This would be methanal, the first one. And then benzaldehyde is its common name, but it's also its IUPAC name. So we call it benzaldehyde all the time. You notice the carbon of benzaldehyde, the carbon of the carbonyl can't be in the ring, of course. We said aldehydes can't be in a ring, but it's attached to the ring.
I have a question.
Uh-huh.
How come it's not like wouldn't it be a phenol? Like phenyl methanol kind of?
So
Or
if you wanted to name it as the parent chain, like this one, be a methanal and then a phenyl group attached, yes. So it'd be a phenyl methanal. But like toluene, we didn't call it a methylbenzene, right? Some people do, but we gave it a special name, right? So most of these benzene-containing molecules, the more simple ones like this, tend to adopt a special name, and they always use it. It's kind of like a common name, I guess, but it's been adopted as the standard name.
okay.
It's just a pain. I know you got to memorize all these benzene names, but it's just a pain. Okay, how about ketones? Slightly different. This time, the longest carbon chain must include the carbonyl carbon again, but it will almost never be on number 1. Why can't it be on number 1? Because if it were at the end of the chain, it wouldn't be a ketone, it would be an aldehyde. Right? That should make sense, right? It can't. This one had to be at the end because we couldn't attach 2 carbons to it. This one must not be at the end because we must attach 2 carbons to it. So it's almost never number 1. It's usually in the center of the chain somewhere, right? Well, not necessarily the exact center, but not at the ends. Right? And you give it the number that would give it the lowest number, so which end you count from would decide which end is number 1. Right? Now, unlike aldehydes, ketones could be in rings. And if they are in a ring, then the carbon, let me go back to one and show you, the carbon of the carbonyl is number one of the ring, much like we did with alcohols. It was defined as number one. So if you put a ketone in a ring like this, that carbon is number one by default. Now you could go either way around the ring and give other things the lower number possible, but this is number one in a ring for ketones. And that's kind of the only place you're going to find ketones as number one, because they can't be at the ends of chains. Okay? So how do we deal with their name? We treat it the same way. We drop the final E. Instead of adding al for aldehyde, we add one for ketone, right? O-N-E for ketone. All right, so we've been pulling features of the class name into the IUPAC names to remind you what they are. Like alcohols have the OL ending, aldehydes have an AL ending, and ketones have an ONE ending to match their names. So these should be pretty simple. All right, so some examples down below. These are common names I don't want you to memorize. It's a very simple common naming system, but we're going to use the IUPAC system. And so let's name these two by their IUPAC names. Right? Not the ones below, these are common names. So let's name these two properly. So the one on the left, find the longest continuous carbon chain that must include this carbon. Doesn't have to start at it, but it must include it.
Butane.
Butane, it'd be 4, right? So it's butane, and we changed the ending from E to "one," so it'd be called, don't skip a syllable.
Butone.
You skipped a syllable.
Butanone.
Butanone, right? It's very common that I hear people skip that middle syllable. That's why I said it. So you're not the first to do it. You won't be the last. Right? So all we're dropping is the E, not the whole last A-N-E. Right? So there's an additional syllable now. So instead of butane, it's butanone. Right? So both syllables are still there. All three are still there. Okay, so 1, 2, 3, 4. We're going to start on number 1 on this end. 2, 3, 4. So in butanone, do I need to tell you where it is? For aldehydes, it was not necessary. It's always number 1. What about here?
Yes.
Yes.
Why?
Yes.
Why would I need to tell me?
For not that one, because it's automatically going to be.
So normally I would need to tell you.
Right?
Right. Normally I would need to tell you for the reason that it's not necessarily number 1. I agree, because it could be somewhere else. But in this specific example, it can't possibly be anywhere else. Because if I were to put it on the end, it would no longer be a ketone, so I can't do that. Can't put it on this end, it would no longer be a ketone. If I put it here, what I'm looking at is number 3, it would actually be number 2 from the other end and the same molecule. So in this particular case, I don't need that 2 to tell you where it is. But for most ketones, you will. Right? In this particular case, I won't. How about the next molecule? Right? So find the longest continuous chain that must include this carbon. And I gave you these examples on purpose to show you some exceptions to the pattern.
The butane chain?
How'd you get 4?
Because there is one carbon included in the ring, and the other side at the end as well.
So you're either in the ring or you're not. You can't count from one to the other. They're separate clubs. So this carbon is not in this chain. It's in the ring. So this is a 6-membered ring, and this is a 3-carbon chain. Remember, this is not a carbon, it's just a bond between them. So what's the longest chain here that must include this carbon?
Propane.
3, right? 3 carbons long. So propane, we changed the ending to
Propanone.
propanone, right? Just drop the E and add "one." So 1, 2, 3. And this is unusual because it is on number 1, right? And it's on number 1 because it has a substituent on it. And I can't include this carbon in the chain because, like she was saying, it's in the ring. It can't be in the main chain. Okay, so 1, 2, 3, propanone. That's the main name of it. What's on my propanone? This is a substituent now.
Cyclo. Like 3-cyclo. Propanone.
So what's the name of the thing as a substituent. It's not just a cyclo.
Okay, cyclohexene.
It's a cyclohexyl, right? And it's on number
3.
1.
On number.
So number 1. All right, this gets the lowest number. So you can't start here and give it 1, 2, 3. It's 1, 2, 3. I said carbonyl carbon will almost never be on number 1, but there are exceptions.
Tricky.
And the reason this is because I gave this example on purpose, is because something has been attached here to replace the hydrogen that was there, and so I can't call it an aldehyde anymore. So it is a ketone. Okay, so just follow the rule. This has to be the longest chain that must include this carbon. You can't go into and out of rings. So 1, 2, 3, propanone. And on number 1 is a big cyclohexyl group. Okay, so it's 1 cyclohexyl propanone.
I have a question.
Uh-huh.
So why would I thought you said with the ketone, like you couldn't, like the oxygen like attached to it couldn't be number 1. I mean the carbon. Oh, oxygen. I'm so dumb. Sorry.
The oxygen can't be number 1 because it's not a carbon. Right? You can't call this number 1. That's not a carbon atom. But this is number 1.
How do you spell that? Would it be like PROPANONE?
Yeah, just drop the final E of propane and then add
Okay.
ONE. This doesn't replace the other letters, just the final E.
Okay.
Right, so propanone. Let's do some examples then.
Could you repeat the first one as well?
The first molecule here.
Yes.
So it's 4 carbons, so you write butane, but leave off the final E and write ONE. So butanone. BUTANONE.
Is that the whole name?
That would be the whole name for that one, yeah. The numbering is unnecessary because it can't be anywhere but 2 and still be a ketone. Okay, so let's look at a few more down here. Here's 3 more examples at the bottom. These are common ketone names. You probably have heard of these before. The first one is the simplest ketone there is. It's called acetone. It's in old-fashioned nail polish remover and such. The newer versions of nail polish remover have an ester in it instead, an ethyl acetate ester. But older versions have acetone in them. And they're much more harsh on your skin, but they're a little more effective. But acetone is the simplest ketone there is because it uses the fewest number of carbons to make a ketone, which would be 3. Right? But its IUPAC name is not acetone. What would it be? Name this guy. Find the longest continuous chain that must include this carbon.
Propanone?
Propanone, exactly. So propane, we drop the E, we add ONE. So propanone. Do I need to tell you where it is?
No.
No, I don't have to tell you it's on number 2 because it can't possibly be anywhere else. If it were on the ends, it would be an aldehyde. Right? So acetone's proper IUPAC name is propanone. Right? How about the next one? We call it acetophenone. Right? But what does it look like? What would you try to name it if we followed our rules strictly? We know the benzene rings get weird names, but what would you try to name this? The longest chain.
Ethanol.
Say again?
Ethanol. Ethanol.
So ethanone, right? So 2 carbons, 1, 2.
Yeah.
With what attached?
Benzene.
A benzene ring would be called
Phenyl.
phenyl group as a
Phenyl.
substituent, right? Not phenol, but phenyl, right? So a phenyl group attached to a ethanone, right? But as usual, the benzene names, their more common names have been adopted, or easier to say. So acetophenone is the one we use for this one. Do I want you to memorize that? You don't have to for these, for the ketones. There's just so many of them, right? And then the last one on the right has 2 benzene rings attached to a 1 carbon ketone. That's kind of weird to say, right? Because how could it have just 1 carbon? But it does, the one in the center, and there's 2 benzene rings attached to it, right? So this is a benzophenone. Instead of acetophenone, it's called benzophenone, right? Or a diphenylmethanone, right? Is another name for it. But you don't have to memorize those names. I'm just showing you examples. The ones I want you to try to do are on this page. Okay, the very first one, again, using those benzene rings, I don't ask you to name that one, but you should recognize it as a ketone. Right, the highest priority thing in this molecule is still that carbonyl. It's higher priority than anything you've seen. Right, so I don't expect you to name this one because I said you don't have to learn the benzene name for this one, but know it's a ketone.
Excuse me.
Uh-huh.
You're going to let us know which ones we need to memorize?
Yes, so everyone I've shown you so far, except these two.
The first one is a dimethyl ketone, an acetone, and a propanone, like it's called all three.
Yes, so dimethyl ketone is the common way of naming these things, and they all end in the word ketone, which is a very easy thing to do, but it's a common name. You don't have to learn common names. Acetone is another common name for it that's been used forever because it's very old. It's been recognized for a long time what this molecule and this compound is. But I want you to know it's IUPAC names for all of these. Right? So this one would be called a propanone. Okay? These over here, the acetophenone and benzophenone, are the two I said you don't have to memorize these two benzene names. We've got enough already. Let's not add any more. Right? So we did some last time with the phenols and the anisols, and I just gave you one up here with the benzaldehyde. Right? It's the only one with the aldehyde. But that's enough. Let's not add any more to it. So you don't have to know these two. I'm just showing you that you should recognize them as ketones, however. That's what this is saying here. Right, so let's finish doing some examples. How about the one on the far right with the chlorine on it? The first thing you should ask is, what is the highest priority thing in the molecule?
The ketone
So why do you think it's a ketone?
with aldehyde.
It's an aldehyde. Right? So there is an H here that's not H here that's not drawn. Okay, so it's often seen this way. Your microphone's still on. So it's often seen this way where you have a carbon with the oxygen double bonded, carbonyl, and then there's a hydrogen here. We don't have to draw hydrogens on carbons. Right? So this one does have an H. How do I know it's there? Because carbon makes 4 bonds. So I know this has 1, 2, 3, and 1 more bond. Right? Whereas the one above, I know there was no hydrogen here because I can see 4 bonds. Right? So this is an aldehyde, which makes this carbon number 1 by default. And so what's the longest chain starting here?
Butane?
Butane, right? So for butane, I changed the ending to
Butanol.
so butanal with an AL ending, right? And then what's attached to my butanal?
Chlorine,
A chlorine, and you call that what as a substituent?
Chloro.
chloro,
A chloro, and where is it?
Chloro.
I heard somebody say it.
3-chloro.
It's on number 3. Do I need the 3?
Yes.
Yes.
No.
Because?
It could be on 2.
It could have been on the 2 or also the 1, maybe.
Well, it can't be on, well, it could be on 1, but it could be on 2, could be on 4, right? It could be some other place. It could be on 4, in fact, right? Because that's not a carbon. So it can be elsewhere, is all you have to answer. And so, yes, I need the number. So it's going to be 3-chlorobutanal. Okay, how about the one at the bottom? First, identify your highest priority thing.
The ketone, carbonyl, carbon.
So the carbonyl is the highest priority thing, and in this case it is a ketone because there's no H left on here. So this carbon must be in the main chain. It's not necessarily number 1, right, like aldehydes are. So what's the longest chain that must include this one?
Butane.
Right, 4, once again,
Butane.
butane, and I'll change the ending to own. So it
Butanone.
becomes butanone. Do I have to tell you it's on number 2?
No.
Yes,
Why?
because it could be on. We could be on number 3.
If you take this O away and put it here on number 3,
Oh, it's gonna be the same.
it's going to
because
be
it's
the
gonna
same.
be turned around.
Exactly. So that's great. You have to see that for yourself. So you put this O here, and it would actually still be on number 2. Right? So I don't need the number because it can't possibly be anywhere else. That's really hard to get sometimes until you see it yourself. Right?
Can you explain like the hydrogen on the first one we did, and then like how there's like not a hydrogen on the second one?
How many bonds does carbon make? Always.
4.
4. So looking at this one on the right, how many bonds do you see to this carbon? I see 2 to the oxygen, right? 1 to this carbon, and that's it. I don't see any more bonds. So there must be a hydrogen to make the 4th bond. Whereas the one at the bottom, I explicitly see 4 bonds. 2 to the oxygen, 1 to the carbon to its right, and 1 to the carbon to its left. Right, so sometimes the hydrogen is drawn, like it is on the last example on the left, but sometimes you don't draw it. So hydrogens on carbon don't have to be drawn. It's optional. Hydrogens on anything else must be drawn. Okay, how about the one on the far left? Highest priority thing.
The aldehyde.
The aldehyde's carbonyl, exactly. So right there, this carbon must be number 1. So what's the longest chain?
Fentanyl.
All right, so 5. 1, 2, 3, 4, 5. Pentane, we changed the ending to al, so pentanal. Right, I'm stressing the al on purpose so you don't hear all. Right, so I know if you say it quickly, it sounds the same. So pentanal, and what else is on my pentanal?
A methyl.
And its location?
2.
So 2-methyl pentanal. Any questions on these 4? Or the bottom 3 at least?
Why wouldn't it on butanol? Why doesn't it matter where the number is at, like the 2?
So on the one at the bottom, we're labeling it from right to left. 1, 2, 3, 4. With me so far?
Yes.
And where else could this oxygen have been? Well, you're thinking maybe it could be on 3, right?
Mm-hmm.
So erase it here in your mind and redraw it down here on number 3. Okay, so this doesn't exist in your mind, and redraw it here. Isn't that the same molecule if I start counting from this end?
Yes.
So it's still on 2.
Okay.
Right? So if it's the same thing from the other end, it's the same molecule. So it's just this whole thing flipped around. So you can't go more than halfway into a molecule. Same thing we did with alcohols. Right? So we can't put this on number 1 or number 4. That's this trick here, because then it's no longer a ketone. It can't be on the ends. So it only can be in one place, one of the interior carbons. That's why it's unneeded.
Oh. Okay.
Right.
I didn't get it before, but like when you said that it could be flipped around, I understood it then.
Right. So it's a little more restrictive than alcohols because it can't go on the ends here, or otherwise it would be an aldehyde. So ketones are restricted to interior carbons. Okay. Let's do some more examples. How about the top left? This one's very easy.
Heptanal.
Heptanal, right. So find the highest priority thing would be your carbonyl. So this carbon, since there is an H here, it's an aldehyde. Right? How do I know there's an H? I count bonds, right? So 1, 2, 3, there must be a 4th bond, so it's an H. Right? Sometimes it's drawn explicitly, sometimes it's not. So this is 1, 2, 3, 4, 5, 6, 7. So 7 carbons long is heptane. I changed the ending to Al, so heptanal. Why do I not need to tell you it's on number 1?
They have to be first in the chain.
Right. If it's an aldehyde, it's by default on number 1. Can't possibly be anywhere else. Okay. How about the one on the top right? Very similar. This is like learning a foreign language.
2-methylheptanol.
So 2-methyl
Heptanol.
heptanol again, exactly. So same thing, I just added a methyl group on number 2. That doesn't make the chain any longer, right? Even if I added an ethyl group here, it would not make the chain longer because I must start here. Right? Because aldehydes by default are your highest priority, you must include this carbon, and for an aldehyde it must be number 1. Okay?
Excuse me.
How about the bottom left? Let's try this ring structure down here.
I have a question on the second one.
Okay.
Why wouldn't you change the heptanol to hept with an E? Because there's a double bond.
Sorry, I couldn't quite make out what you said.
Why wouldn't you change it to an E in the heptanol when there's a double bond?
So the double bond you're asking about, why don't I make this an E in the name, like an alkene?
Yes.
An alkene is a double bond between carbons. This double bond does not involve 2 carbons. It's a carbon and an oxygen. This is not
okay.
This is not a
Thank
member
you.
of the main chain. It's an oxygen.
Right. Okay, thank you.
Good. Okay, how about the bottom left one with the ring?
Oxo. I know it's a ketone, but I don't
Okay,
know.
let's just build up the name slowly. It's 8-membered ring. You got that. This carbon must be in it, in the main chain. So we get the 8-membered ring. So 8 is octane. It's a ring, so you call it cyclooctane. Then just drop the last E and put -one. So cyclooctanone. Right? It's easier to write than to say sometimes, I know. Especially when you have multiple letters back to back that are the same. But, so cyclooctanone. And then what is this? It's a fluoro on 2. So when I chose this in the ring as the main chain, this is automatically number 1. That's unusual for ketones, but in a ring it will be number 1, right? Because it's the highest priority thing. And I could have gone around the ring either way. And you chose to go this way to give the fluorine a lower possible number than if I went the other way, right? It'd be on 8. So 2 is better than 8 because this is still at number 1 either way. So it's 2-fluoro, don't misspell fluoro, right? Cyclooctanone. It's not cyclooctone, don't skip this syllable. Okay, we're only dropping the last E, not the whole last syllable.
So will it always be number 1 in the the ketone in a circle in a ring?
Right, so a ketone in a ring will have to be number 1 if it's the highest priority thing, and it usually will be. Okay, aldehydes cannot be in rings, so of your list so far, ketones are the highest thing that can be in a ring. Right, and then the one on the right, just go slow, find the longest continuous chain that must include the highest priority thing. Well, what's the highest priority thing? Let's do this one step at a time so everybody can follow.
I have a question that's slightly unrelated to what we're doing right now.
Okay,
In regarding the priority list,
yes.
what is above the alcohol group again?
So above alcohols are ketones,
Okay.
and above ketones are aldehydes.
Okay, thank you.
Right. So on the right here, find the highest priority thing. What is it?
Ketone.
Ketone.
Carboxyl.
Right. So the carbonyl.
Carbonyls.
Carbonyl. Right. We'll get to carboxyl groups later. So carbonyls, and in fact there's 2 of them. So if possible, like we did with all the other things, if possible, try to get both of these carbons in the main chain. You can always get one, but if it's possible, get both. And it is here because I'm going to choose the ring, right, as the main chain. So a 6-membered ring as a main chain, what's the parent name going to be? Start very basic, 6-membered ring.
Hexane.
Hexane.
Cyclohexane.
Right, so we'll start with hexane. It's in a ring, cyclohexane. Now let's change our ending. It's a ketone, right? So what do we do?
Hexanone.
Right, so cyclohexanone, but there's 2 of them.
Oh,
How do we indicate 2?
di.
Where do we put the di? That's the important question.
Hexanone.
In front of the what?
In front of the hexanone.
Are there 2 hexanones?
No.
Are there 2 hexanones? 2 hexanones. 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 2 h
No.
No, where do we put the di?
Cyclohexane.
Before the known.
Right in front of the ending, right in front of the own. Just like we did with alcohols. We didn't call them dialcohols, we called them diols, right? We put it right in front of the ending. So here you have cyclohexane and then a dione as the ending. So we leave the E on there this time because it makes it easier to pronounce. And then we add the dione ending. Okay, so cyclohexane dione. Where are they?
One and four.
Do I need to tell you that?
Wouldn't this make it?
Yes.
Yes, because I do have to tell you that. When there's only one, it's obvious it's on number one. But when there's two of them, they could have been on, say, 1 and 2, or 1 and 3, or 1 and 4. Right? So I need to tell you the 1 and 4, absolutely. And then very last thing, what is this? I have some substituents.
2, 3 bromo.
2, 3, how many bromos?
Dibromo.
Right.
Dibromo.
Right. So 2, 3, because I could choose either one as number 1 and go through these two to get to the other, so they're going to be on 2 and 3. So 2, 3, dibromo, and then 1, 4, cyclohexane dione. Quite a long name.
Did you say para?
You can't use para here. Why not?
Because of the bromine?
No, not because of the bromines. Ortho, meta, and para were reserved for whom?
Benzene rings?
Benzene rings. This is not a benzene ring. You cannot have a carbonyl on a benzene ring. Tell me why.
Too many bonds.
Right, it would make 5 bonds to carbon. So absolutely right. So no ortho, meta, or para here. You just call it 1, 4. I know para means 1, 4, but it's reserved for benzene rings. Okay, so this one's a longer name to build it up. We started off very simple, but we applied the exact same rules all the way through. And this 2, 3 dibromo and the 1, 4 and putting the di in front of the ending, you've done all that before. You just have a new ending. That's the only thing we've added. So this is like learning a foreign language. You've applied all the grammar rules you already know. You just learned a new word. Right? So it's a new higher priority word. That's all this means. Okay. So let's do a couple more here. Remember, I don't want you to memorize acetophenone, but this is acetophenone. And the only thing I've done to it is added a chloro group on number 2. So 1, 2, there's a chlorine on it, right? So chloroacetophenone. Again, you don't have to memorize acetophenone. But the one on the right, you should be able to name this. Right? I know the name's written there, but let's look at it and decide what this name would be on its own. Find the highest priority thing in this molecule. What is it?
The carbonyl.
The carbonyl, highest priority. And is it an aldehyde or a ketone?
Aldehyde.
Right, there's at least one H on it, so it's an aldehyde, so this must be number 1. So what's the longest continuous chain starting here? 1, 2, 3. So we're going to call it what? What are we going to start with?
Propanol.
So propane. All right, we'll start with propane, just 3 in a row. But it's an aldehyde, so I changed the ending to not propane, but propanal, right? So P-R-O-P-A-N-A-L. I changed the E to an A-L. But there is a double bond in it. It's no longer my highest priority. The aldehyde's higher priority, but I must tell you about it. So what do you do with this double bond here? How does it change the name?
Propane.
Right, it changes the A to an E, just like we've been doing with alkenes. So instead of being propanal, it's propenal. Right? E for the double bond and the Al ending instead of E for the aldehyde. We know the aldehydes by default are number 1. Why don't I have to tell you where this double bond is? I didn't put a 2 in front of here.
It can't be anywhere else.
Exactly. Where else would it be? It's either on number 1 or on number 2. Right? There is no number 4, so it can't possibly be on 3. And it can't be on 1 because there's not enough bonds to put a double bond there and still be an aldehyde. So it must be on number 2, so don't need to tell you, it's the only place it can be. right? Is this cis or trans possible? I'm not asking is it cis or is it trans. I'm asking is it possible to be cis or trans here?
No, because there would be two hydrogens would be the same on one side.
Right, so the left side has differences, right? There's this thing and an H, I agree. But the right side has two H's, and those aren't different from each other, so cis and trans are not possible here. Excellent. And a little story I put on the slide for you. You don't have to memorize this reaction. We'll talk about these type of reactions later in biochemistry, but you don't have to memorize this one for today. But if you have molecules that are exposed to tissues, in this case to your eyes, the mucosal membrane of your eyes, they can interact with enzymes and other molecules there and create irritants, right? And so one of those irritants, when you're cutting onions, for example, when you're cutting an onion, which is a plant with cells in it, and you break those cells open, and inside those cells are enzymes in the onion, and they interact with lots of molecules from the onion. Here's one of those molecules. You don't have to name it or anything, just looking at it. And we're going to take it and break some bonds here. This enzyme alanase does that. It cuts off this bond here and so forth, right? And it breaks it up into this molecule here, right? And then another molecule in your eye, right? An enzyme in your eye converts this, which is volatile, right? It floats in the air in the room where you're chopping onions, right? It's harmless to most surfaces, but if it gets in your eye, which it will if you're in the room, right? Then your eye's enzyme will convert this molecule to the one on the right, so it's moved a double bond around a little bit, right? And this is very reactive with water, right? And there's water in your eye, right? Because it's a mucous membrane, so it interacts with water and transforms into sulfuric acid, right? Or sulfates here, plus this molecule on the right. So name the one on the right down here. What is this thing here? It's an aldehyde. This is what irritates your eye and makes you cry.
Propanol. Propanol.
Propanol, right? Because it's an aldehyde, so 1, 2, 3, simple propanol. Not like this one with the double bond, just a single bond version. So propanol. And propanol is an irritant to your eye. So not many of these molecules make their way through the air to your eye. You don't want to rub the onion juice in your eye. That would be a bad idea, right? But a few of these are aerosolized and get into your eye and react with the water there and form this propanol and the sulfuric acid. Right? And that combination irritates your eye. Some people don't cry when they chop onions, right? Why not? Because they don't make abundance of this enzyme, right, in their mucosal membranes. So this molecule is still in the air, it just doesn't turn into these irritants for those people. Some people make a lot of this, so if they're anywhere in the house and you're chopping onions, they'll know, because it converts rather quickly. Right? So it's just an idea to show you that aldehydes and other carbonyls are involved in things in everyday life. And some other common aldehydes and ketones that you're familiar with, the simplest pair, formaldehyde, the simplest aldehyde, and acetone on the right are propanone, right? The simplest ketone. Right? So how do we get these molecules? And I mentioned it before, right, on a previous lecture when we talked about alcohols. If I take a primary alcohol like methanol, right? This methanol has one carbon, it's got 3 H's on it and 1 OH, and I did that process called oxidation. Go back and look at that slide again. Right? If I oxidize it once, I said an easy way to remember it was to make the carbons making more bonds to oxygen and fewer bonds to hydrogen. And that's exactly what we've done. So if you take methanol with the OL ending, the alcohol, and oxidize it once, you get formaldehyde or methanal. Okay? And this is the aldehyde used in preservatives. You may have seen some old jars in your biology lab or in an anatomy lab. It's an older anatomy lab that uses formaldehyde to preserve tissue. Okay. The simplest ketone is again the same type of thing. It's oxidized from a secondary alcohol because secondary alcohols make ketones. Primary alcohols made aldehydes. There's still an H left. So this one, if you start with 2-propanol, right, which is just like this, except instead of this carbonyl, it's just an OH here. There is 1 H left, right? And we oxidize it. So secondary alcohols, go back and look at that chart, become ketones, and that would make 2-propanol. into acetone or propanone. Right? And propanone or acetone is a very simple organic solvent. It's kind of volatile. You smelled acetone before. Right? And it mixes well. It dissolves both polar and some nonpolar things. So it's kind of a great solvent. Right? It dissolves many things, including the membranes on your cells. So if you pour acetone on your skin, which is a bad idea, it'll dry out the membranes and your hands will crack and everything else. So it's not a good thing to keep around on your skin. Right? But if you have someone and you detect acetone either on their breath or in their urine, this is very bad. Right? It's usually one of two things have happened. If I smell acetone on someone's breath, right? Well, one of three things, I guess, two of which are equivalently bad. So if I smell acetone on someone's breath, either they've been drinking acetone, which call the morgue because they have an appointment, right? Or they've been drinking isopropanol, which is not quite as bad, but still a very bad idea, right? Because isopropanol, if you drink it, much like any alcohol, if you drink it, it gets oxidized in the liver. So this would become acetone in the liver, which will dissolve away the liver membrane. So if you're drinking isopropanol, they're going to die rather quickly, right? Ethanol is not much worse. It just takes a little bit more to cause the same problems. But if you smell acetone on someone's breath and immediately ask them, have you been drinking rubbing alcohol? Please hope they say no. Because then there's a lesser cause and it could be just an indication of diabetes, right? Which is way less than imminent death. Right? So when you have a patient, which you're working to become medical professionals, most of you, and you smell their breath, you're going to have to do this as medical professionals, and smell their urine, right? And if you smell acetone in it, you better ask them what they've been drinking, because sometimes, lots of people run out of drinks in the cabinet, and they go in the shed and start drinking rubbing alcohol, or bathroom and drink rubbing alcohol because they think it's the same, and it's not, right? Or less dangerous and less immediately deadly is they're actually a diabetic or an alcoholic. Right, so another one, less grim things to talk about. These are better flavors. These are also aldehydes and ketones. And they're all part of these molecules. And I showed you a picture on a previous lecture of all these molecules and asked you not to worry about them. We were looking at the benzene ring parts of them. But they also are aldehydes, like this vanillin at the top right. Right? It's got 3 different functional groups you should be familiar with now. Yes, there's a benzene ring in the middle, but it's got an aldehyde group at the top. Right? It's got an alcohol group at the bottom, the hydroxy down here. And it's got an ether on the right, this methoxy, right? And those 3 combinations put together give you the flavor of vanilla, right? There's a receptor on your tongue for that flavor. The one right below it is get another aldehyde. It's attached to a benzene ring, but it's got a double bond in the middle. And this long chain here is what gives cinnamon its flavor. It's trans-cinnamaldehyde. Right? If this bond were cis, it wouldn't have that flavor because your receptor doesn't recognize it. The one in the center is our simple benzaldehyde, and it's the flavor of almonds, or if you get a really concentrated benzaldehyde, it tastes like or smells like cherries or cherry pits. Right? It's used as a preservative in food. Right? The one on the top left is called citral because of this bond being trans here. Right? If it were cis, it's not quite as strong a flavor. But this is in lemongrass and orange peel and lemon peel, and it gives you that citrus flavor. Right, in the peels of those fruits. Right, underneath the bottom one is a ketone. You can easily name this one. Right, you can name all of these, in fact. But this one's a ketone. Right, it's 2-heptanone. It's the flavor of cloves. The one in the center is much like we did earlier. Our butanone. It's just got 2 of them on numbers 2 and 3. Numbers not needed. Where else would they be? Right, so it's 4 carbons long and ketones on 2 and 3. So it's a butane dione, and this is the flavor of butter. This is what permeates movie theaters, this molecule, right? That flavor of hot butter smell. Right? This is what you're smelling, that molecule. And on the right is carvone. It's the flavor in spearmint, right? This is not the same thing as wintergreen. Everybody makes that mistake. So spearmint and wintergreen are not even remotely close to the same thing. Spearmint is this molecule. It's a ketone, right, with all these other double bonds in it and such. Wintergreen's actually an ester you'll make in lab later in the semester. They smell quite different. Right? And then lastly, we'll talk about where we find ketones in some of our hormones. right? So these three hormones, which are all made from cholesterol in the body, and you see that 4-ring steroid structure in the center. It's 4 fused rings, they all sharing a side, right? That's the core of any steroid, including cholesterol. Right? But these three are all ketone hormones. Right? So on the left, you have testosterone made in the testes and produced during formation of male secondary sex characteristics and such. Also responsible for aggression if you make too much of it. But you notice it has an OH up here at the top right, so that's a hydroxy group, making it an alcohol, but we don't call it testosterol, it's testosterone because this is the highest priority thing, that ketone, right, down here on the bottom. Progesterone, another hormone made from cholesterol, as all these are, has 2 ketones on it, right? So you can tell these two apart rather easily if I showed you their structures. You may not be able to draw them yet, but testosterone has 1 ketone, progesterone has 2, 1 on each end. And thirdly, cortisone, to the own ending, not cortisol, cortisone has 3 ketones on it. So 1, 2, or 3, you can tell these apart rather easily if I showed you their structures.
I have a quick question. When people go on the keto diet and they test like ketones in their urine, what ketones are being tested? Like, is it just like a basic ketone?
So it's not any of these hormone ketones they're talking about. That diet is meant to reduce your consumption of sugars, right, and force you to use alternative molecules as food sources. We'll actually get to that later with our biochemistry part. But it's using molecules in metabolism, not necessarily these hormones or other organic molecules we're talking about, but they have ketone-like properties, right? So they contain that carbonyl functional group. That's all that means.